Hello students, welcome back. Let us resume our discussion in section 6, Polynomial Congruence. We went through just one example, this motivating example, but this example is actually quite important because it gives you two very important ideas. First, the reduction by Chinese remainder theorem. Modulo 200 can be decomposed into 5 squared times 2 to the third power. We have two prime factors here. So using the Chinese remainder theorem, you can decompose this congruence into two simpler congruences. Now, if you had not just two, but say 20 prime factors, then we will have 20 congruences. 20 congruences of the form some prime to the certain power, p to the k form. So here, 5 to the second power form, and this one is 2 to the third power form. So you can reduce using Chinese remainder theorem and solve those separately and then patch them back later. So the key is to solve congruence for p to a certain k power in general. Okay, all right. The Chinese remainder theorem that allows us to do the first reduction. How about the second reduction? This is going to be a bit tougher. In this case, we have just simpler case. Oh, not this one. Mod 25, so 5 squares to mod 5. And then we use this kind of technique using the binomial theorem to expand out. And the key part, quadratic or higher, will just disappear. Remember that? Even if this is 30th power, it doesn't make any difference. Quadratic or higher will just disappear. So we have the constant term and the linear term, and that's it. So the computation for this binomial is not outrageous. Definitely something you can handle. And for humongously large numbers, maybe not you, but something computers can handle. And then, after all these reductions, divide by 5, and then mod 25 reduces down to mod 5, and then, how to handle from that point on. And this kind of reduction technique can apply not just 5 squared down to 5, or p squared down to p, but as a matter of fact, any p to the k power down to p to the k minus 1 power, and then down to p to the k minus 2 power, all the way down, down, down recursively to just mod p. So same technique applied over and over and over again, recursively. But then again, establishing all that is not that easy. We need some lemmas, Taylor's theorem, and then Hensel's lemma, that's even more significant. But in the end, what we want is this summary. Let p be a prime, and let R be a solution of the polynomial congruence. F of x is congruent to 0 mod p. So that's the base case. In other words, here, f of R is congruent to 0. Then the solution of this f of x is congruent to 0 mod p to the k power, the kth generation follows from some additional condition here, which is a big restriction as a matter of fact. If the derivative evaluated R is not congruent to 0, then you cannot use this. You have to do some other reduction, which is in many cases possible, but you have to do it case by case. Let's not consider those kind of things. And under this new condition, the solution for mod p to the k power, which we name as rk, can be obtained recursively like this. Rk is rk minus 1 minus f of rk minus 1 times, let's see, what is this? F prime of r, this one here, which is non-zero mod p, and p is prime, therefore f prime of r and p is relatively prime. Consequently, we have multiplicative inverse. So this additional condition yields this f prime of R inverse. As a matter of fact, I should have specified that. Is a multiplicative inverse of f prime of R modulo p. Not modulo p to the k power or k minus 1 power. It is modulo p. That's something I should have emphasized. Okay, I'll correct that in the real notebook. And then as for the proof, well, we're going to need all these lemmas, so let's not worry about those yet. We're going to come back and do those proofs in some optional videos later. For now, let's just focus upon how to utilize this. Let's see, do we have an example problem here? Okay, here's a good one. X to the third power plus x squared plus 29 is congruent to 0 modulo 25. Okay, all right. Let's work out similarly as the motivating example. First reduction, mod 25 down to mod 5. For mod 5, well, you can use just brute force computation, right? You can try x is 0, 1, 2, 3, and 4. There are only 5 numbers to try. And x is 0, that's trivial. F of 1, nearly as trivial. F of 4, which is f of negative 1, almost as trivial. And two non-trivial computation, f of 2 and f of 3. In this case, it turns out f of 3 is congruent to 0. All those are easy computations, even for humans, so I'll leave those to you. In any case, for base case, use brute force to find out. All right, we got it. Now let's apply Hensel's theorem. All right, for base case, f of 3, so R value is 3. And then what do you need? R prime of 3 should be non-zero, otherwise we cannot use Hensel's theorem. And then we need its multiplicative inverse. Okay, that's our first goal. Step 1 is to find f prime of R and then its inverse. Okay, what's f prime of R? Well, just take the derivative. Here 29 is reduced to 4 modulo 25. No, excuse me. 29 is reduced to 4 modulo 5, but mod 25, oh, that too is just 5. But anyway, doesn't matter. The constant term will disappear if you take the derivative. It's gonna be what? What's gonna be the derivative? F of x is 3x squared plus 2x, right? So if you do f of r, f of 3, then you're gonna have 3 here and then 3 there. And this computation, that's not too bad. You can do that. If you do it, that's what you're gonna get. So previously, r is equal to 3. Okay, we got that. And then we need f prime of r. So put it into derivative and do your computation. And then that turned out to be 3. So take its multiplicative inverse, modulo p. In this case, modulo 5. Oops, sorry. I cannot undo. Sorry about that. So f prime of r inverse f prime of 3. It's 2. That's what it is, isn't it? 2 times 3 is 6. And that's congruent to 5. Congruent to 1 modulo 5, excuse me. And this thing okay, all right, we got it back. So we're going to put in 2 right here. How about r k minus 1? Well, r is 3. Next, we have to find out r1, but that's easy. r1 is equal to r, so that's going to be 3. And then we need, f of r1. Let's work it out. R1 is 3. F of R1, just plug in 3 in place of x here and there. And then 29 is congruent to 4 modulo 25. So eventually we are going to get 15. Do you like this computation? All right. If everything fits, that's going to go right here, 15. And then 3 right here. That's just step 3. So let's see. This one here, f of r1 is 15. And that's going to go right here, green. Therefore, R2 is recursitively R1 minus f of R1, and then the derivative, inverse of the derivative, and then put it into this. And this thing here, f of R1 is 15. And in step 1, we did f prime of R inverse is 2. So we did this in step 1, we did this in step 2, and then put everything together into this Hensel's theorem. Barely everything is in the same viewing window, and do your computation. You're going to get 23. It's not a difficult computation, you can do it. By the way, here's the verification by Mathematica. Here I'm trying all possibilities, all 25 entries, case running from 0 to 24, and I'm calculating modulo, so mod operation, f of k mod 25. So the remainder of f of k when divided by 25. And that's 0 when k is 23 right here. We have a unique solution here. Now, if we start from not just f of r is 0, something else, f of s is also equal to 0, then you'll have to do something similar to that. Then that too will be a solution, so we may have multiple solutions there. But if you start from the unique solution, as in this case, just one solution here in the base case, then in the end, you'll still get unique solution. And why do we have unique solution that way? That's something we'll have to answer when we prove this Hensel's theorem, which we're going to do a bit later, probably as an optional video. So we went through one example, and I'd like to repeat a couple more times, but not enough time. So let's stop here, and then let's do part B and part C in a separate video. See you soon.